This lecture is part of an online course of multivariable calculus, and I'm going to talk about two applications of double integrals. So let me start. The first one would be finding the area of the region R. So finding area of a region R. Okay, so how do I do that? Because the region R is in 2D, and basically when we have the double integral of f dA over any region R, we are calculating the volume of a solid bounded by R and F. Okay, so basically if you have the region R in here, and then if you have your function f on top, okay, the volume of this solid would give you the double integral. Okay, but notice that if we have a box like this, if it is a good box like that, and then this is the region R, if the height of the box is 1, then the volume would be what? Would be the area of the base, which would be R times the height. The height would be 1, so basically the volume of this box in here would be the area of the region R. So now inside the double integral, if instead of f we have 1 instead of the volume of this solid, it's just because the height of the solid is 1, we just have the area of the region R. So it would be the double integral of 1 dA over the region R. So we give the height 1, and then we find the volume of the solid with the height 1. It gives us the area of the base. Okay, let me just quickly say the second application would be finding the average value of the function f of x and y in the region R. Okay, it is what? It's 1 over the area of R, and then the double integral of f of x and y dA over the region R. Okay, let me give you just a small recall that the average value of just a single variable function, it would be 1 over b minus a, the integral from a to b of fx dx. Okay, so if we just have one function, a single variable function like that, from a to b, okay, then this formula gave us the average value of the function on the interval a and b. So when we have the region R, we have kind of like the same thing. 1 over, instead of the length of the interval, we have the area of R, and then the double integral like that. Okay, so let me give you some examples for each one of them. Example 1, find the area of this shape. Okay, let me graph the shape like this. This is x-axis, this is y-axis, and okay, this is 5, this is 6, and then this is the region R that I have in here. Okay, I want to find the area that is in here using the double integral. It's just because it would be easier if you remember, the area in here would be, this is, I consider half of the circle of radius 6, which would be what? Which would be pi 6 squared, and then half of it, and then I'm gonna subtract the disk of radius 5 in here, so it would be 1/2 pi 5 squared. Okay, just using the simple geometry. But using the double integral, the area of R is the double integral of 1 dA over R. It's what? I just need to set up the bounds, and since the region R is part of a circle, it's better to use it polar. If I want to use polar, I'm gonna write dA as R dr d theta. Now finds the bounds for R. For I, I'm gonna graph a ray. This is the first point to hit the region, so it would be R equals to 5. This is the second point to hit the region, R equals to 6. And then theta would be the first ray that I write in here. So theta would be from 0 up to pi. Okay, so let me calculate this. This is from theta equals 0 to theta equals to pi. Then the inside integral in here would be r squared over 2, r from 5 to 6 d theta. So this is theta from 0 to pi. Plug in r equals to 6 in here, so it would be 6 squared over 2 minus 5 squared over 2, and then d theta. So this is just a constant, so 6 squared over 2 minus 5 squared over 2 times theta from 0 to pi. So it would be 1/2 6 squared minus 5 squared times pi. As you see that these two are the same. Okay, now let's solve one example of the average value. Find the average value of the function f of x and y equals to x squared plus y squared to the power of 3 over 2 over the region R, which is in the first quadrant and bounded by y equals to 0, y equals to root 3x, and the circle x squared plus y squared equals to 9. Okay? The first thing that we always need to do is to graph whatever region that you're given. So let me graph the region R in here. X-axis, y-axis. And then it's part of the circle x squared plus y squared equals to 9. So it's a circle centered at the origin of radius 3. And it's bounded by y equals to 0, which is basically x-axis, and y equals to root 3x. So let me graph that line in here. So this is something somewhere like here, just assume this is y equals to root 3x, and it's bounded by x-axis here, the circle of radius 3, and y equals to root 3x. So this is the region R. Okay, this is R equals to 3. And okay, now we want to find the average value. So the average of f over the region R has a formula. It's 1 over area of R, and then double integral of f dA over the region R. Okay, so let's find area of R first. Area of R. How do I do that? Well, I know that to find the area of a region R, I can use the double integral. So the double integral of 1 and then dA. dA is just because we have part of a disk, it would be easier to do it in polar. R dr d theta. Now let's find the bounds for R and theta. As you see that R, if I graph a ray in here, R starts at 0 and it goes up to 3. So r0, r equals to 3. How about theta? Theta is starting at 0 at this ray x-axis, but it goes up to y equals to root 3. So I'm gonna say y equals to x. I'm gonna divide both sides by x, which is tan of theta in polar. It's equal to root 3, and therefore theta equals to pi over 3. Okay, so this theta that I have in here, this theta is pi over 3. Okay, so it goes up to theta equals to pi over 3. Now let me calculate that. The integral from 0 to pi over 3. Let me just move this one a little bit so that I have more space. There you go. And the inner integral would be the integral of r dr, which would be r squared over 2, r from 0 to 3, and then d theta. So it would be what? Theta from 0 to theta equals to pi over 3. Plug in 3 for r, 9 over 2 minus 0, d theta. So I get 9 over 2 times theta from 0 to pi over 3. So this is 9 over 2 times pi over 3. So this is 3 pi over 2. That's the area of the region R. So this is 3 pi over 2. Now, for the rest of my formula, I need the double integral of the function f. Okay, let's calculate that one as well. So the double integral of f dA over r is what? The function f is x squared plus y squared to the power of 3 over 2. X squared plus y squared to the power of 3 over 2 dA over r. I'm gonna switch it into polar because r is just a part of a disk. That's why it's easier to do it in polar. So I get r squared for here to the power of 3 over 2. For dA, I'm gonna do r dr d theta, and then the bounds for r would be the same, r from 0 to r equals to 3, and then theta from 0 to theta equals to pi over 3. Okay, so if I want to simplify this one, it would be r squared to the power of 3 times 3 over 2, so it would be r cubed. Okay, I have another r in here that's gonna multiply by that, so everything together would be r to the fourth. So now this integral here would be theta from 0 to theta pi over 3, and now the answer for the inner integral would be r to the power of 5 over 5, r from 0 to 3, don't forget d theta, from 0 to pi over 3. Plug in 3 in here, so it would be 3 to the power of 5 over 5 minus 0, and then d theta, so it would be 81 over 5 times theta from 0 to pi over 3, so it would be 81 pi over 15. Yeah, so this is the answer for this double integral in here. So the average would be 1 over the area, so let me write it in here. It would be 1 over the area is 3 pi over 2 times the double integral of f, which is this one, 81 pi over, oh no, I made a mistake. This is 81, actually this is 3 to the power of 5, and then when I divide it, so this is that was theta. So this is 3 to the power of 5 over 5 times pi over 3. So now one of them would be cancelled with 3 of that, which would be 81 pi over 5. Okay, and I'm gonna replace it in here. I'm gonna simplify this one and that one, 3 and 81, so I get 2 is gonna come up, so 2 times 27 over 5, so the answer would be 54 over 5.